The chapter about trigonometric integrals have 2 subchapters. Integrals with trigs, those guys. So they have trigs in it. And integrals that require trigs to solve them. So that was this one. If I go back to integration, as you can see, U-sub, integration by parts, we figured out. And then 6.2. Part 1, integration that has trigs, that's what we're going to do now. And then using trigs to actually solve the integral. That means integral did not have any trigs, and somehow we assumed it was a good idea to plug the trig inside. That's what we did. So the second one is harder, it's time consuming, sometimes it's very long. You see this beautiful decoration. Look at this. Remember we did this was the first example, and the right triangle and everything like that. So there was a table there which basically asks you to memorize this piece. If you see a constant squared minus input squared, then plug constant sign. If you see an input squared minus constant squared, then plug constant secant. And the only one with plus will be tangent. That's how I memorize it. The only one with plus is tangent. Let's go back. So either integrals have trigs, or you use trigs, plug them in the integral and use properties or identities to help yourself out. Sine squared plus cosine squared is 1, and secant squared minus tangent squared is 1. So you use those and it works out. Let's practice these first. Those goes faster. How do we work with integral of sine square or integral of cosine square? We had them so many times already, you should know. How do we work with integrals with sine square and cosine square? Yes? Cosine of what x? Squared x? Oh, thank you. We're going to do this for this one. You're right. We're going to separate cosine's cube as cosine square and cosine, change 1 to sine, 1 minus sine square. Not for this one. For these ones, when you just have one standing cosine square or one standing sine square, we're using what? Double angle formula, half angle formula, those two works. In this case, double angle formula. Now let me review both. Double angle formula says if you have cosine square x, it will be 1/2, 1 plus, cosine likes cosine, double x inside. If you have sine square x, it will be 1/2, 1 minus, it's still cosine, cosine 2x, like so. Use these. Basically, they also have, these two formulas have a name, a power reduction formula. Because we know how to integrate cosine of 2x. So if you use this formula, we're reducing the power. So the name is the power reduction formula. That gives us an integral of 1/2, I like to take it out, 1 minus, no plus, cosine of 2x. And that is easy to integrate. It will be 1/2 x plus or minus, what is integral of cosine? Plus sign or minus sign? Plus sign. How do I know? Because when I differentiate sign, it gives you plus cosine. So it's going to be 1/2 x plus 1/2 sine 2x. Anything is missing? Divided by the leading coefficient. Exactly. You see, the answer follows right away. This is a good example. It's fast, requires to know the formula. If it was too fast, we can review later slowly or practice. We had this example everywhere. Calculus 3 will have it everywhere. Differential equations will have it everywhere. It's a popular formula. Cosine square and sine square, they recreate circles and circular motions, so they do appear everywhere. Everywhere. But this one, you're right. How to rewrite sine cube so we can integrate it nicely. Integral of sine cube and whatever is inside, it's linear, we don't care, it's U-substitution. It's important to have even power. So let's have it. Sine square of 3x. And the left over, I like to call it a tail. Sine x 3x. Why? Because the tail will be your du in the u substitution. If sine 3x dx is du, I know that u should be cosine, plus or minus. It's called scaled. Some multiplied by negative sign, this doesn't matter. So du is in front of you. Now you need to figure out the u instead. So it's reverse logic here. If du is sine, where is my u? It should be cosine. Well, I will figure it out by shifting from sine squared to 1 minus cosine squared. That's from the formula sine squared plus cosine squared equals 1. It's over here. Cosine squared and sine squared can jump to another function if you needed to. So it becomes integral of 1 minus cosine square of 3x times, I will still put it in different color, sine 3x dx. Then I for sure can see I want u to be cosine 3x. This is u. Because then I know the integral will be 1 minus u squared. Make sense? That's what I want to see. When you use u substitution, you should have some kind of future vision in next 2 steps at least. 1 minus u squared. Can I integrate this? Yes. If the answer is no, maybe don't do u substitution. Maybe it will make it worse. Then du will be, derivative of cosine is minus sine 3x over 3. Correct or not? Multiply by 3. So don't forget, that's a common mistake I saw on a test. It is times derivative of the function inside times the leading coefficient. When you differentiate, you multiply. When you integrate, you divide, because integration undoes differentiation. dx. Again, u substitution happens here. So I need this sine 3x dx. But I have minus, let's see, I have minus sine 3x times 3 dx. So solve for it, or just multiply and divide by negative 3. If I'm solving, then I know that sine 3x dx, that's what I need in yellow, will be minus 1 over 3 du. Plug the first and the third equation into the integral. Then it will be u is cosine 3x, and then du will be sine 3x dx, but also over minus 3. Equal sign 1 minus u squared, I can integrate that, that's doable, times minus 1/3 du. That is what the tail over there gave me. And that's how we choose. We knew what u should be because the tail was there first. I know how to integrate that. What is integral of 1? That is u. Go back to the previous function. So minus 1/3, I'll factor it out. Integral of 1 is u, but u is cosine 3x. Integral of minus u squared is minus u cubed over 3, but u is cosine 3x. So it's going to be cosine 3x cubed over 3. That is the answer. What do you think about that? That is how to integrate functions with trigs. There are more complicated cases like this, but we can do them later. The whole idea which I want to say is this. The idea is the same. We're going to do it later, but the idea the same. I like even powers. Keep it as it is. I don't like odd power. Even powers are good because this is sine square x to the 3. And sine square is minus 1. And sine square is 1 minus cosine square. So I can jump between functions sine and cosine using even powers. I don't like odd powers. That's how I know that cosine better be written as cosine squared times cosine. Now I know that cosine dx will be du, so u will be sine. Which one do I need to jump to another variable? Cosine 1 minus u. That's how it's going to be. No, it's going to be u, and sine square will be 1 minus blah, blah, blah. So we're going to do that later as well. So the exception is this guy. Cosine square and sine square standing by itself, we use double angle formula. But these, all the products, are usually done by creating a tail that will have us even powers. And even powers help us to jump between functions, sine and cosine, tangent and secant. We're going to do more, so if it's challenging, start practicing it now. But we're going to keep reviewing. Don't postpone to the last moment.